Good. We are live. Okay. So let's get started. So we will continue our discussion on spectral methods. This will be the fourth lecture on this module. And we started off with discussing the adjacency matrix, then a little bit about the Laplacian, and then we moved on to the random walk matrix, which is actually the most interesting matrix of all. So let's do a quick recap of what we did last time. So this lecture and the next lecture will deal heavily with the random walk matrix. So I'll do a quick recap now. If any of you have questions and stuff, please do stop and ask me. Yeah. So what was a random walk matrix? So it was a generalization. First, we worked with sort of undirected graphs. So undirected or directed graphs. So we either way. So unweighted graphs. The random walk matrix was just this matrix WG given by DG inverse AG. It was the matrix which sort of represented the probability that you go from a vertex I to a vertex J. It sort of represented this. And this, once you write it this way, it naturally generalizes to weighted graphs. Weighted graphs with all non-negative weights. Non-negative weights, you could have the same definition DG inverse AG, where DG, the degree of a vertex in this case, is defined to be the degree of a vertex is the sum of the edges that go out of the vertex U and U. That was what was defined to be the degree. So we could work with this notion of a degree. And the random walk matrix had the following properties. That is, the all ones vector was a right eigenvector. So it was sort of an averaging operator. So if you had the all ones was a right eigenvector, and the fact that it was non-negative just told us that W UV is greater than or equal to 0 for all U and V. In fact, these are the only requirements for a random walk matrix. So we sort of generalized and we said we'll work with this sort of random walk matrix. This is the only requirements of a random walk matrix. That is, it is the all ones is a right eigenvector, and it's a right eigenvector of this matrix, and all its entries are non-negative. Requirements for any random walk matrix. So let's go with that. That's the matrix. And we defined, and we saw there was a nice distribution called the stationary distribution, which was a function pi going from the vertices to the reals. Summation pi v is 1. And it was just given with pi v is proportional to the degree of a vertex. More precisely, pi v is the one which is equal to degree of a vertex by summation of degree of u. It was u. It was this distribution. By the way, over here itself, you should have asked me a question. To write DG inverse, so out here, somebody should have pointed this out. To write DG inverse, when can I write this? I can write this only if there's one condition. When can I write DG inverse? This is always a valid definition.
When the determinant is not 0.
Determinant is not 0, but this is a diagonal matrix. DG is just the diagonal matrix. It has all this one. So when is the determinant non-zero in this case?
Should be connected.
Connected.
Is it connectedness?
I mean, sorry, like each entry, I mean, you shouldn't have any vertex with degree 0.
Yeah, that's all. So we are working with things in which, so So random walk matrix, if there's any vertex with degree 0, that means you never step out of that vertex. So if you give me a graph that has such things, we'll just knock them off. We'll just throw off these isolated vertices and work with the resulting graph. So it's not only an unweighted graph, but it's a weighted graph with no isolated vertices. Otherwise, DG inverse doesn't make sense. So every vertex has a non-zero degree, and that's why I can write DG inverse. So if you give me a graph in which there are vertices of degree 0, it doesn't matter. Those don't contribute to the random walk. We'll just knock them off in one shot. So even if some of you have seen the problem set, there will be one of the, if you have already seen the problem set already, there will be one of the problems in which we actually assume that the graph has no isolated vertices, because that causes issues while doing these things. And one of the issues is primarily some of the definitions just fail to hold, because we'll be talking about DG inverse often enough when DG inverse doesn't exist. Okay, so we had this, and we wanted to understand, so this was a stationary distribution. I'm going to this. And the key thing about the stationary distribution was pi transpose W was pi transpose. So last time I used pi V, pi. So my vectors are always column vectors. So last time I said I wrote it as pi. So that was wrong. It was when I meant pi transpose. Okay, so this was the key. So in other words, these are it's a left eigenvector of W with eigenvalue 1. Now we have one right eigenvector, one left eigenvector. To understand the spectrum, we would like to know if there's a full eigen decomposition. And for this, we knew from the spectral theorem, if the matrix W was self-adjoint under some inner product, then we do get not only an eigen decomposition, we actually get an orthonormal eigen decomposition. So we wanted to work with a particular this one, and there the inner product which we considered there, all of this is a recap from last time, is instead of the usual dot product, we work with the inner product Fg pi, which is in which you weight each vector by the stationary distribution. Because this is the stationary distribution, you want to sort of give relative weights. Instead of talking about the usual dot product, which gives the uniform distribution and all the thing, we're going to sort of work with this dot product, work with this inner product. This is also valid inner product. And we wanted to know when does W, what is self-adjoint of W under this. We notice that the self-adjoint of W under this is exactly the time reverse probability, time reverse walk. Therefore, W is self-adjoint. We notice that W is self-adjoint. So we had this notion of reversible random walks. Which is stating that pi U equals W UV is the same as pi V WBU for all UV vertices. So this was sometimes called the detailed balance condition, the time reversible condition, or whatever. These are multiple names for this. And this condition is equivalent to stating that W is equal to W star. It's a self-adjoint under this inner product. Under this inner product. Therefore, the spectral theorem tells us that we have a full eigen decomposition. And so let's call the eigen decomposition. Let the eigenvectors be W1, W2. We'll put them in decreasing order. Omega 1, omega 2, omega n. These are in Rn. These are in R. And the corresponding eigenvectors. So these are eigenvalues. Of W, and these are the right eigenvectors. Corresponding right eigenvectors of W are V1, V2, Vn. These are elements in Rn. So we had this, and furthermore, these were actually orthonormal. under this inner product. What we do know is one of the eigenvalues, omega 1s, is 1, and the corresponding eigenvector is the all 1s. But this is an averaging operator. Therefore, we know that the largest eigenvalue in magnitude can be at most 1. It's an averaging this one. Therefore, in fact, it's not just one of the eigenvalues. It is the largest eigenvalue is 1. So omega 1 is the all 1s. And V1, this is the corresponding, this eigenvector is the all 1s. And not only this, because it's an averaging thing, it's not just it's at most 1, its absolute value is at most 1. Therefore, omega n is greater than -1. So all the eigenvalues of the random walk matrix are in between 1 and -1. So -1, I do not know if it is achieved, but 1 is achieved, and the corresponding eigenvector is the all 1s vector. This is the right eigenvector. So this is where we had stopped last time. This is the entire right eigenspace. Starts off with 1 and goes this one. What we wanted to do is understand the left eigenvectors. That is, we wanted to ask what are the vectors. Notice eigenvalues, left eigenvalues, right eigenvalues make no sense. They will be the same set of eigenvalues. The question is eigenvectors. What are this one? What are the eigenvectors? What are the vectors v1 prime all the way up to vn prime, such that vi prime transpose w is equal to vi prime, or equivalently w transpose vi prime. So, and this is omega I vi prime. This is what we want to find out. We know one of them is the stationary distribution with corresponding eigenvalue 1. But I want to lay my hands on all of them. So let's stare at what we have already. We already know that W is self-adjoint. So we have FWG is equal to WFG for all FG on the vertices. We have this. Now I want to write something about W transpose. So let's write FWG. So let's write each of these guys. What is FWG? FWG, we saw that it was exactly pi v, FV, GV over V in V. This is the same thing as F transpose pi G, where pi is diag of the stationary distribution. Are people with me on this? So just written it this way. The reason I'm writing it this way, I want to get transposes into the picture so that W transpose will not come in. So let's write down WFG in the same this one. So if you notice, that will just be, with the same token, it will be WF transpose pi G, which is F transpose W transpose pi G.
Wait, sorry, I'm
In the
confused.
first,
There's no W in the
yeah.
first expression.
Sorry, there is no W in the first expression. You are right. So this is. So what I wanted to write was this one. Just let's first write FG. GV. This is F transpose pi G. And now I want to write. So this is this one, and FWG. That's got me. This is F transpose pi WG. Making a mistake over here. Okay. And this is that is this. And we know that these two are always equal. So since reversibility, Reversibility implies F transpose pi WG is equal to F transpose W transpose pi G for all Fg. This, if you notice, will just imply that pi W has to be equal to W transpose pi. Because you could set F to be the indicator of EV and G to be the indicator of EU. Take this and element by element, you'll realize that these two vectors will be actually, these two matrices have to be the same. So this tells you that is W transpose is exactly pi W pi inverse. So it's take W, it's pre and post multiplied by the appropriate diagonal matrices. One is the reciprocal of the probability stationary distribution, another is exactly the stationary distribution. So from this, I want to claim that we can actually, once we have this form for W transpose, it will immediately tell you what are the eigenvectors of W transpose. So what do we know? We know for each V in V, W V. So I did this mistake. So let's call for each I in V. I'm going to index the vectors with I because I call the eigenvectors V. So we have the WVI is omega I VI. Now let's define VI prime to be pi VI. And let's look at what happens to W transpose VI prime. What is this? This is pi W pi inverse, and this is just pi VI. Expanding both. W transpose was pi W pi inverse. This is pi VI. Pi and pi get, pi inverse and pi get cancelled. You have WVI. So this is pi of WVI. WVI I know is omega I VI. So this is just omega I pi VI, which is just omega I VI prime. So what do we get out of this? We get that if V1, V2, Vn are eigenvector, are right eigenvectors, pi V1, pi V2, pi Vn are the left eigenvectors. And this makes sense. One was the all ones eigenvector, the eigenvector corresponding to all ones. Pi, when you multiply that by pi, you get the stationary distribution. That is the corresponding left eigenvector. We also knew the stationary distribution was a left eigenvector. So one was the right eigenvector, the corresponding left eigenvector was the stationary distribution. So it was just one being multiplied, the all ones vector being multiplied by pi. And the claim is this is not just true for the all ones, it's true for every single of the other eigenvectors. Therefore, the claim is the fact is this. Therefore, the left eigenvectors are in fact pi, which is just pi of all ones, then pi V2, pi Vn with eigenvalues 1 equals omega 1 greater than omega 2, and omega n, which is minus 1, is greater than minus 1. So is that okay? Any questions? So we understand, but notice the left eigenvectors are not necessarily orthonormal. Only the right eigenvectors are orthonormal. Right eigenvectors were what we were given. Nobody said the left eigenvectors, but these are the left eigenvectors for this random walk matrix. Is this okay? So these are the left eigenvectors. And the key property which we just used was this property. Pi V is W transpose pi. Now this pi V W transpose pi, I want to actually stare at it a little longer. So what do we have? We have pi V, I said is W transpose pi. Now, what is pi W transpose? Pi W transpose is W transpose pi transpose. By definition, transpose of a product is the product of transposes. But But W transpose, pi is a diagonal matrix. Therefore, this is just W transpose pi. Therefore, this is just, and this we know as pi W. Therefore, pi W is a symmetric matrix. Now, why am I doing this? Why am I doing all of this? What's the random walk matrix? The random walk matrix was W, which I can write as pi inverse pi W. This seems an utterly ridiculous way to write a random walk matrix. Why would I write pi inverse as pi W? But notice this is very similar to, I had written DG inverse. This was how I had written for unweighted graphs. This was how we had defined. Recall this definition. AG was just the matrix of weights, and then I had pre-multiplied it by the diagonal matrix corresponding to the degrees. Now I'm claiming that you take any random walk matrix, it looks like pi inverse of pi W. This is almost the same as DG inverse AG. That is, pi W is a symmetric matrix. So, and pi inverse is almost the degree this one, except the fact it is normalized. The sum of the degrees is 1 because it's a problem. That's, in fact, that's the only difference between this representation and this representation. The fact that the sum of the degree vectors is 1, whereas there the sum of the degree vectors could be some arbitrary positive real number. So what this tells you is any reversible matrix. So we started off. What did we start off with? We started off with regular unweighted graphs, regular unweighted undirected graphs. Then we sort of removed the regularity condition and we went to arbitrary irregular unweighted undirected graphs. Then we said, okay, fine, we'll work with irregular weighted, no, irregular doesn't, just weighted undirected graphs. And then we even more generalized, we go to random walk matrices. And among random walk matrices, we considered special kinds of random walk matrices called reversible matrices. But now what I'm saying, any reversible matrix has underlying in it a weighted undirected graph. Basically, the weighted undirected graph, the weights are exactly pi W. So what I'm claiming is, give me a reversible matrix, reversible random walk. Underlying in it, there is a sort of a graph, a weighted graph, this underlying this walk W, where the weights are exactly pi given by pi W. That's the matrix. The only difference between this adjacency matrix and the other adjacency matrix is the sum of the degrees is normalized to 1. But modulo that fact, this is exact. So all I'm claiming is this generalization, which we went from weighted undirected graphs to reversible matrices, is not a generalization. In fact, these are the same object. Any reversible random walk matrix is in fact a weighted undirected graph. So if you're saying weighted this one, you can actually, when somebody says a reversible random walk, you can just draw the graph in which you have just weights on all the edges. These weights don't represent the probability from going from one vertex to another. They represent the product of pi u into the product. It's not just a transition probability. That is the random walk matrix. The weights over here, the adjacency matrix weights refers to the probability that you first pick the left endpoint and then take the step, or the right endpoint and then take the step. These are both the same because it's reversible. Okay, so why am I sort of stressing this? When people say reversible random walks and all, you don't have to think. It's water. When they say reversible random walks, all they mean is a weighted undirected graph. That's what is going on background. So you can just say you're working with a weighted undirected graph. There's nothing. There's no this one. Non-reversible are a different beast. We will not get into them. Firstly, I don't have, the spectral theorem does not apply to them. They will have to do things to sort of we don't have the entire toolkit of spectral theorem, the spectrum of these graphs to work with. So they will do things they won't work with the random walk matrix. The random walk, they will sort of work with a related matrix, which actually is self-adjoint, and try to get the spectrum and see if it has this one. And sometimes even that doesn't work. So those of you who possibly attended Schulman's talk in the STCS symposium, he was in fact working with, one of the main points of his talk was to talk about random walk matrices which are not necessarily reversible and try to see how to analyze them. The usual way of analyzing them is try to come up with a related reversible random walk matrix, get properties from it and derive it. And he was trying to say sometimes this is not good enough. But anyway, this is beyond what we wanted to do. We are working only with reversible random walks, which are equivalent, by what our discussion is, equivalent to weighted undirected graphs. Reversible random walks are weighted undirected graphs. Any questions? Okay. So reversible undirected walks, and this are in fact, these are equal. These, all I'm claiming is these are equivalent motions. And that's an important point. It's a trivial observation, but it's a useful observation. So when people say reversible Markov chain, all you have to think is there's a weighted undirected graph underlying, and the weights are not the probability transitions, but it is the stationary times the probability transition. Okay. That's some remarks, which furthermore remarks I want to remarks about for observations on the eigenvalues. The first observation, we already saw 1 was equal to the largest eigenvector omega 1, and this is greater than W2, omega 2. A question we can ask is, when are omega 1 and omega 2? Can omega 2 be equal to 1? Omega 2 be equal to 1. And suppose the graph has 2 components. Suppose the graph, the underlying random walk. So we're working with just reversible walks. So it's an undirected graph, and we can talk now over the components of this graph. So once I'm given I'm talking about reversible random walks because of this equivalence which we mentioned above. There's an underlying graph, and you can talk about whether the underlying graph has 1 component, 2 components, or several components. Suppose it had 2 components. Now, I want to claim that any vector which is all ones on 1 component and 0 elsewhere is an eigenvector with eigenvalue 1. Because take a vector which is all ones on any 1 component and 0 on all the other components. Rather, any vector which is constant on each component is an eigenvector corresponding to the eigenvalue 1. So in particular, the number of eigenvectors, and notice that if you take ones on 1 component, 0 elsewhere, these are orthogonal eigenvectors. They are even in the pi inner product, they are going to give you, they are going to be orthogonal to each other. So in particular, the eigenspace corresponding to the 1 eigenvalue will be at least the number of components. It will at least be the number of components. So what we want, it's not hard to see, is the number of the dimension. What I said just now was just the dimension of the eigenspace corresponding to the 1 eigenvector is at least the number of components. You can go the other direction also. Suppose the graph was connected. Suppose the graph was connected. I claim if the graph is connected, the only eigenvector corresponding to the all ones, to the eigenvalue 1, has to be the constant eigenvector. Now, suppose, so if the graph is disconnected, we know the dimension of the eigenspace is at least the number of components. So in particular, omega 2 is equal to omega 1 if the graph is disconnected. If the graph is connected, at every vertex, the eigenvalue has to, so give me any eigenvector, its value should be equal to the average of its neighbors. This should be throughout. So you will notice that within each connected component, this will force the values all to be the same. In particular, any eigenvector corresponding to all one's thing has to have the same value within each component because it's the average of this. Therefore, if the graph is connected, there can only be the eigenvector corresponding to the all ones can be only of dimension 1. So this is actually not just any greater than or equality, this is an equality. Because the eigenvector corresponding to all ones has to have the property that within each component, the eigenvector's value at each vertex should be the average of its neighbors. Therefore, this will have to tell you if it's corresponding to the eigenvalue 1. This average, the only way it can be is the eigenvector should be constant within each component. This what does this tell you? If the underlying graph is connected, then 1 is then omega 1, which was 1, is strictly greater than omega 2. And this is an important observation to keep in mind. And what we will do actually towards end of today's lecture and the most of next lecture will be to understand, we will measure, so this is a spectral notion of connectedness. Omega 2 being apart from 1 tells you whether the graph is connected or not. We will give a combinatorial notion of connectedness called the conductance. And we'll compare these two notions and show what we have shown is the combinatorial notion will have the property if the graph is connected, then that conductance will be non-zero. If the graph is not connected, then it will be 0 if the graph is disconnected. But that will also be a quantitative measure, and we'll relate these two quantitative measures via what are called the Cheeger inequalities. That will be for the next lecture. Other thing, but before that, I want to do a couple of more sort of preparation for that. One thing is omega n. Omega n we saw was always greater than -1. Now, if a graph is bipartite, if the underlying graph are bipartite, then there is an obvious choice for omega n. What is the corresponding eigenvector? You can take 1 on the left side and -1 on the right side. This, because each one is an average of the other, when you take the average this way, everything over here, so you have a left and right, this average will go to everything on 1 here will become -1 here, -1 here. If the 1s and -1s will just shift to this one. So notice that all I'm saying is if the underlying graph is bipartite, then omega n in fact is equal to -1. So the graph is bipartite, omega n, there is an eigenvector corresponding to putting 1s on all the left one side and -1 on all the other side. This will correspond to eigenvector. This will be an eigenvector and the corresponding eigenvalue will be -1. Now it's not hard to see. Suppose you now I want to ask the other direction. Suppose omega n is equal to -1. What you will see in the next problem set, this is actually the other direction is also true. So this will be in problem set 4. So, in problem set 2, you did it that if you look at the adjacency matrix, nu n, I think there was something, nu n being equal, what was it? Mu n equals -mu1 if and only if the graph is bipartite was one of the problems. This is going to be the corresponding thing for not just the adjacency matrix, even for the random walk matrix will have the same property. So what we'll do in the rest of today's lecture will be trying to understand how well does the random walk mix. So you start off with, of course, if you're with the stationary distribution, you start with the stationary distribution and you take steps according to the stationary distribution. You will continue to be in the stationary distribution. That's the property of the stationary distribution. Now, suppose you didn't start with the stationary distribution, you started with some other distribution. Suppose you started with a distribution that put all its weight on just one vertex. And then you began taking a random walk based on this random walk matrix. From there, you chose a random neighbor based on the weights. And then you went to something. And from there, you chose a random neighbor and you did this walk for t steps. And I want to ask what happens to this walk. What happens to this walk? Of course, it's going to be a different probability distribution on the entire set of vertices. What we will show, there are two things which are going to happen. We're going to ask, does this random walk eventually converge to a single random walk, to a single distribution? Of course, if it converges to a distribution, it has to converge to the stationary distribution. Because if it converges, that means you take the next step, the probability distribution does not change. Then that means that has to be a left eigenvector, and that has to be the stationary distribution. So if it converges, it has to converge to the stationary distribution, to a stationary distribution. Now the question is, does it converge at all? Now there are some reasons why the graph, this might not converge. For example, if it's a disconnected graph, there is no way it's going to converge, because if you start from a vertex in one component and you keep mixing, it will never hit a vertex in another component. You will never go to another component. So let's see what are the bottlenecks. I'm going to just ask, what are the bottlenecks for mixing? One bottleneck is the underlying graph is disconnected. So certainly if omega 2 were equal to omega 1, if omega 2 were also equal to 1, we don't expect this walk to converge. Because if you start in a distribution that is just for all its support in one component, it will never, at no point of time will the distribution ever put any weight on the other components. So first thing, if you want to ask about convergence, omega 2 should be separated away from omega 1. So it should be smaller than 1. That's one bottleneck. The other bottleneck I want to say is bipartiteness. If the underlying graph was bipartite, and if you supported everything on one side, the first step will take you everything to the second side. That's what the random walk will do. The next step will take you to this side. So the random walk is going to sort of keep going back and forth. This will never converge, because on odd steps, you're going to be on the right side of the graph. On the even steps, you're going to be on the left side of the graph. This is something which is never going to converge. So bipartiteness is another bottleneck for convergence. So the underlying graph being bipartite. So let's try to get rid of these two bottlenecks. What we'll assume that both omega 2 is separated from 1, omega n is separated from minus 1. If we assume these two bottlenecks are out, and so we'll define this quantity called omega, which is the maximum of omega 2 and minus omega n. And we want to say if omega is less than 1, somehow the walk is going to converge. So that's going to be what we're going to show next. So if omega is less than 1, then the random walk converges. Informally, this is what we're going to do. So that is omega 2 is equal to 1, and that is omega n equals minus 1. So this is removing both bottlenecks. people with me so far?
So here we want that for any starting distribution over the vertices, we want the random walk to converge.
Ideally, I would like to do that. For doing that, at the very least, omega 2 has to be separated from 1 because there are starting distributions not converge. Omega n has to be separated from -1 because if these two conditions were true, certainly there are starting distributions which will not converge to the stationary distribution.
Right.
And what we will show surprisingly is once you remove these two bottlenecks, it actually does converge. Any starting distribution will converge to the stationary distribution. In fact, notice we have to be cautious when we say stationary distribution. Question is there the stationary distribution or a stationary distribution? So we all ask, are there multiple distributions pi such that pi w equals pi? Pi transpose w equals pi transpose. W2 being separated from 1 tells you that the stationary distribution is unique. Because if there are multiple of them, that eigenspace will have dimension larger than 1. The fact, so because if omega 2 is separated from 1, we can talk about something called the stationary distribution. There's only one distribution which will have the property that pi transpose w equals pi. Not just the distribution. In fact, there exists only one dimensional. There's only one dimensional space. Even if you allow negative quantities in this one, there's only one vector which satisfies up to normalization, which satisfies that pi transpose w equals pi transpose if omega 2 is separated from 1. But this is not sufficient for convergence because convergence, this will tell you there is the stationary distribution. Even if you have the stationary distribution, for example, a connected bipartite graph, it might not converge because the walk will just keep going between the left side and the right side. You might ask, is the same thing true if the graph was tripartite? We'll see the proof and realize the proof actually handles those cases. Okay. Okay, so what we want to ask, so we're going to remove these two bottlenecks. We are going to work with a reversible random walk in which omega 2 and minus omega n are separated from 1. They are both away from 1. In other words, omega is some quantity less than 1. We are going to use the spectral decomposition to actually ask what happens. So let's do the setup for this. P naught is some initial distribution on vertices, possibly supported on only one vertex. And then we define for t going from 1 to infinity, we define pt to be pt transpose is pt minus 1 transpose times w. It's that. You take a step with the walk, what's the new distribution? Okay. And what we want to ask, the question we want to ask is, does pt converge to pi? That's the question we want to ask actually. Now notice these two are two probability distributions. A natural thing to look at convergence is the total variation distance between the two probability distributions, and we try to analyze this quantity. We try to analyze what's the total variation distance between pt and pi. Does this quantity go to 0? Notice it can never become 0, because if it becomes 0 at any point, that means at the previous step also it was pi, and you can keep tracking back, so it should have been pi all the way from the very beginning. It will never become 0. It will become close. All you can expect, it becomes close, smaller and smaller to 0. You will never, pt can never become pi, because if pt becomes pi at one step, it should have been pi at the previous step also, and so on. You will get this sort of a This one. So what we are interested is the total variation distance how do you spell variation? V-A-R-I-A. Is that right? Variation distance between PT and pi. Usually denoted as dTV PT pi. Notice this is exactly half of the L1 norm between PT and pi. That's the usual. It's the half of the L1 norm between PT and pi. Now, L1 norm is not a nice thing to work with in this one. It's usually, we have seen that inner product, the L2 norm, but also in the pi world is something we can work with. So what I'm going to try to do is the next few steps is convert this L1 norm, or rather upper bound this L1 norm in terms of the L2 norm, but in the pi inner product world, not the usual dot product world, but in the pi inner product. So we'll do a couple of translations. So PT, let's just do it over here. So this half, I'm going to write this as, so this quantity, what was written over here, this is summation up over V and V, PTV minus pi V, the absolute value difference. That's what the total variation distance, the L1 norm between it. I want to sort of not take the sum with respect to y, I want to take the weighted sum by the probability distribution pi V. That's what we've been usually in. So what we will do this, we'll write this as half of V and V, pi V of PTV by pi V minus 1. Because I want to look at the weighted this one. So this can be written as what? So let's further write this as half of summation V and V pi V. Now this quantity, how do I want to write this? I want to write this as pi inverse PT. It's this vector, its Vth value. This is exactly the same thing. Pi PTV by pi V. Element by element I'm dividing. That's same thing as pi inverse of PTV. And you'll soon see why I'm doing this. This is just the expected value according to the pi distribution of the one norm of the vector of just, let me write this. This is just the one norm of the vector pi inverse PT minus V, the one norm, but under the pi. One norm is usually sum of the weights, sum of absolute values of the vector, but I'm going to weight. When I say pi, I mean I'm going to weight it. I'm not going to take the sum, I'm going to take the weighted sum. So this is a definition going on here. So this is actually it. This is a definition, and hope this definition is okay by you. Is this definition okay?
1 instead of V?
What?
Pi, that is a minus V or
Oh,
minus?
sorry, there is no V. That's just the all ones vector. The all ones, what we used all ones. Okay. This is I'm just convenient to work with this. But still notice this is not good enough for us. What we know how to work with is the 2 norm. But Jensen is going to, convexity is going to tell us that this is at most half times pi inverse PT minus 1, the 2 norm of this. And in general, so let's write this definition over here. So So what I want to write, what I mean by any vector v's, that's called any vector phi's k pi. This one is almost the usual definition. It is summation phi v to the power k, and you take the kth root of it, v in v. But you sort of don't take the sum, but you take the weighted sum. And convexity will give you this. So what we'll instead study is we'll look at how, and this will be a nice quantity to work with, pi inverse pt minus 1, the 2 norm. We try to understand how does this quantity change with each step of the random walk. People? Fine. So we'll do the most natural thing. We'll write down PT in its Eigen decomposition, find out what happens to it. And so what do I mean by that? I want to compare pi inverse PT minus 1 2 pi versus pi inverse PT plus 1 minus 1 2 pi, where this is the same as just pi inverse W transpose PT minus 1. Okay. So let's write PT in its eigenbasis. So PT in its eigenbasis. So let's write the probability vector PT in its eigenbasis. Notice that PT is used, comes from, it's on the left, so it's used, but nicer to write it in the left eigenbasis. One thing to notice, this is not an orthogonal eigenbasis, but we'll see that multiplication by pi inverse is going to make things very nicely. So PT, we'll write it as some summation alpha I vi prime. Vi primes are pi vi are the left eigenvectors of W, and vi are the right eigenvectors, which the vi's have a nice one. So PT is this, so I going from 1 to n. This is, let's write it as alpha 1 vi1 plus v1 prime plus I equals 2 to n. Alpha I vi prime. The reason I'm sort of doing this is alpha 1. V1 prime is the pi distribution, summation I equals 2 to n vi prime. And let's write this a little more. This is alpha 1 pi. I should write this a little carefully. This is small pi. This is small pi, which is the distribution, plus summation alpha I pi vi. Now, what is alpha 1? Can someone tell me what?
Sorry, what are column vectors and what are row vectors for you?
Everything are column vectors over here.
So then you write this. Okay.
Everything. So when I wrote the probability, this one, I always PT transpose is equal to PT minus 1 transpose into W.
So pi also is a column vector.
Pi is all vectors are column vectors.
Okay.
All vectors are column vectors. Yeah. Yeah. So I didn't want to keep the thing that probability distributions, I'll make it row vectors and right eigenvectors. Everything is a column vector. Everything is a column vector. Because I want to say that the row eigenvectors are exactly the column eigenvectors multiplied by the matrix pi.
Yeah, so I mean, what threw me off is you're calling it left eigenvector. Its transpose is the left eigenvector, so to say. But it's okay.
So rather, the left, okay, strictly speaking, it is the right eigenvector of W transpose. To be
okay, sorry, go ahead.
The right eigenvector of W transpose. Yeah, if fair enough. Yeah, we've had a discussion on this. The last lecture I did this, but this lecture I wanted to keep this way. Yeah. So what is alpha 1?
1.
Why?
Because pi p is equal to, yeah, I mean,
Why will alpha 1 be 1?
it is the eigenvalue corresponding to the stationary distribution, right? The vector like corresponding to small pi. So,
Yeah, there's multiple ways of seeing it. Possibly the easier, what's the best way to look at this? The best way to see this will be just take the inner product of pi t with the all ones vector. So take this equation which we have here, pi t equals this. Take the inner product of this with the all ones vector. So the left hand side will give you 1, because by the summation of pi t, it's not, sorry, it will not give you 1. Take the sum of the thing. It's not the inner product. The inner product will weigh it again. Take the sum. All I want to say is what's the quickest way to say this? I want to say that observe that alpha 1 has to be equal to what Ishan says is correct. Since PT satisfies summation PTV equals 1, because it's a probability distribution. Once again, there's a quick way to see this. Yeah, the quickest way to see this is look at this vector quantity. Look at this vector quantity. And let's look at this sum. This sum for this left hand side is 1. What is it for this guy? This is just alpha 1. And this guy, if you notice it, each pi vi, if you sum this quantity, what is this? This is summation pi I times summation vi. But vi is orthogonal to pi I. Not orthogonal, vi is orthogonal to the all ones vector. That was the definition. So summation pi I vi is equal to 0. So each of these guys, when you sum them up, they are going to be 0. All I want to claim is, if you look at, and the thing for that,
so you just take the dot product of both sides with the all ones vector instead of the inner product.
The dot product, yeah. So which is exactly this quantity pi vi. I've been using various. This one's pi. pi vi, when let's take the dot product pi vi at the vector u in v. This is exactly summation over u in p pi u viu. This is the inner product between vi and the all ones, which is 0, the pi inner product. And this will tell you alpha 1 is 1. Therefore, in particular, we have, all I have said is pt is equal to pi plus summation I equals 2 to n alpha I pi vi. This is key point to notice. This is the Eigen decomposition, is sort of giving you this sort of a this one. Let's look at, let's similarly write what is pt plus 1. pt plus 1 is by definition w transpose pt, which I will apply on, so that is w transpose of pi plus summation I equals 2 to n alpha I pi vi. This is just pi again. W transpose pi is 1, and this is summation alpha I going from 2 to n W transpose pi vi. But we know that pi vi are the eigenvectors of W transpose. We already saw this with eigenvalue omega i's. So this is pi plus summation I equals 2 to n alpha I omega I pi vi. We have this. Okay. So now let's go back to what we want. We wanted to understand the two norm of pi inverse pi t minus 1, the two norm of this. Let's square it and work with this. This, actually, let me, even before that, we wanted to understand the two norm of this quantity. Therefore, let's write down the quantity we care for, pi inverse pt minus the all ones vector. This is pi inverse pi plus summation I equals 2 to n alpha I pi vi minus the all ones vector. What is pi inverse of v? Is just the all ones vector plus summation alpha I vi minus the all ones vector. Therefore, this is just summation alpha I vi. And similarly, pi inverse of pt plus 1 minus 1 will be, sorry, this is I going from 2 to n. This will be summation I going from 2 to n alpha I omega I vi. But now we are in good shape. What did we want to understand? We want to understand pi inverse of pt minus 1. It's 2 norm. Let's work with this 2 norm square. This is exactly by what we have seen. This is summation I equals 2 to n alpha I vi's 2 norm. This is, vi's are orthogonal, orthonormal in fact. So this is in fact exactly equal to summation I equals 2 to n alpha I square. And by the same exact same argument, pi inverse of pt plus 1 minus 1 to pi 2 is I equals 2 to n omega I square alpha I square. But this tells us immediately, if the omegas were bounded away from 1 and minus 1, if all the omegas, if omega was strictly less than 1, then all the omegas, omega 2 to omega n, are all, or omega 2 square all the way up to omega n square, are all less than omega square. So this quantity will be less than omega square into I equals 2 to n alpha I square, since we defined omega to be the max of omega 2 and minus omega n. This tells you that each time you take a step, this norm shrinks by a factor omega square. And if omega is bounded away from 1, that means each time you take the step, this norm is going to shrink. So eventually it's going to, after significant number of steps, it's going to 0. And this is what we want. And show this will show that eventually what we had talked, this will show that this difference, this quantity, this measure. What's happening? 1 second, something's gone wrong with my. This measure, and this, just give me a second. I'm going to stop sharing and I'll share in a second. You see the string? So all I'm claiming is this quantity, this measure, as you take steps in the random walk, this measure is dropping by a factor omega square, at least by a factor omega square each time. So eventually it will, if omega is bounded away, is smaller than 1, this is going to go to 0. So you can write this. All I'm claiming is, if you put, oh shoot, my pen is giving me problems. All I claim is, if you go back to this one, what did we have? The total variation distance between PT and pi. We had shown that this quantity, what was this? This quantity was at most, this was at most half times the L2 norm between pi inverse PT minus 1, the L2 norm between this, but this is at most, this is maddening. Idea what is happening. This is at most omega. Each time it's falling by, so this is at most omega into pi inverse P0 minus 1 to pi, omega to the power t. Each time it falls by a factor of omega square. Therefore, the square falls by a factor of omega square. Therefore, without the square, it falls by a factor of omega, and this is going to 0. So if you had a bound on this quantity, to begin with, the pi inverse P0, then we can bound the entire quantity. And this quantity, to notice, it's never more than, it's not hard to see that this quantity is at most 1 over square root pi. So let's, my pen is giving me tons of problems. Let's see if I can do something else. Share by AirPlay. No, my Bluetooth is failing me. So this. Sorry about this. 1 second. I don't know what's happening. Yeah, that's the point. Pen has run out of juice completely. Okay, so let it charge for a second. I'm not going to write right now. So what have we? You can this quantity this. So what we care of pi inverse p0 minus 1. We care about the L2 norm of this quantity. If it was large to begin with, anyhow, whatever it was to begin with, the quantity is how much does it reduce by? All I want to claim is this quantity can be at most. So let's assume P0 was supported on just one vector or one vertex. Then what is this quantity? This quantity is exactly, it's -1 on all other vertices. On this particular vertex, it's 1 over pi min minus 1. All vertices, it's -1. On this particular vertex, it's 1 over pi min minus 1. Now notice, any other distribution is just a convex combination of these guys. Therefore, let's take one of this. Let's take one which is supported. I want to claim that this quantity can at most be as large as just 1 over square root of pi min. Take the stationary distribution. Take the vector on which it has the least amount of probability distribution. So that's where 1 over pi at that vertex will be the largest. So we want to find out how large this quantity will be. This quantity can be at most, I want to claim this quantity which I care about is at most 1 over square root pi v, the minimum of this quantity. That is going to be actually, so that is going to be the governing. That's one, it's an initial, some constant thing depending on the stationary distribution. And this, and use that's possibly the worst possible initial separation, the L2 separation between P0 and pi. And that factor keeps reducing by a factor omega with each step of the walk. So I want to claim that for have some case. Another class. Let's see again. This will work. I hope it works. Otherwise, I'll have to do something about the lecture today. Another 10 more minutes. One claim is for any star distribution. P naught I inverse P naught minus 1 over 2 pi is less than or equal to 1 over square root of minimum over all v pi b. That's can be, and we'll just work with that's an upper bound. So this quantity is going to be at most omega t. Then this way, this we'll define it to be what we call pi min. So this is omega t 1 over square root pi min. So eventually, if you want to get the total variation distance be smaller than epsilon, so there is a half. To smaller than epsilon, you take enough number of steps so that this quantity becomes smaller than epsilon. And eventually, as t goes to infinity, this is going to 0. So it says so we saw that if you have a random walk, if omega 2 or omega 2 was close to 1, omega 2 was equal to 1, or omega n was equal to -1, then we knew that the random walk did not converge, because we have the starting distributions which will never converge. But now we show if that were not the case, if you remove these two bottlenecks, the fact that the underlying graph was connected, and the fact that the underlying graph was non-bipartite, if you had made these two starting assumptions, then the graph will converge. Then the random walk will converge to the stationary distribution. And this, in fact, tells you the rate of. It gives you an upper bound on the rate of the convergence. It will at least converge as fast as this. It might converge slightly faster than this, but this is at least at this rate, it will converge to the. So if you want the total variation distance to go smaller than epsilon, you choose t large enough so that this quantity becomes smaller than epsilon. Okay, that's one thing. I wanted to start the Cheeger inequalities. I don't have enough time for it, so let me do something shorter. Which I did not want to do, but let's do it. I'll talk about what's called the expander mixing lemma. So once again, if omega is given a graph, so the expander mixing lemma is going to talk about the following. All of these are easy. All of these are the easy consequences once we know the spectrum of the underlying random walk matrix. So suppose you're given two functions f and g on the set of vertices. We can, and let's define mu f to be the expected value of fb, but when taken according to the pi distribution, that is summation pi v f. Okay. No, and similarly, mu g. I would like to know what fg is. What is fg in the pi walk? Fg. I'm not going to write this. Fwg. This we already saw. This is just take. What was this? This was just pi v wbu fb g. So this is, it's sort of, you can view it equivalently as it's sort of the expectation of f comma g according to pi. So it's this sort of expectation. So it's the easiest way to write this is the expectation of fv gu when you take the first vertex according to pi, the stationary distribution, and u to be according to the random walk starting at v. That's the one. What we would like to compare is I would like to compare this quantity expected fg when I take uv to be an edge. This is what I would, this quantity versus I just take expectation f versus expectation g. That is, in one step, let's look at what the left hand side is stating. Let's look at the right. Left hand side is stating I take a random vertex and I take a random neighbor and look at the expected value of this product. I take a random vertex, compute f on that vertex, take a random step of it, go to u, compute g on it, and take the expected value of this product or the random vertex. What's the right hand side stating? I take a random vertex according to the stationary distribution, compute f on it, take its expectation, then take a random another completely random vertex according to the pi stationary distribution, compute G on it and take its expectation. This will seem as if I'm ignoring the random walk completely. I'm ignoring the random walk. I'm just picking two independent vertices F and G. So this is, I'm going to write this as, this is expectation. I pick V from pi, U from pi, and take FU, GB. So I'm ignoring, I'm just taking two independent copies of the vertices from the stationary distribution. And the first one I'm taking the first vertex from stationary distribution and the second vertex to be a neighbor induce what you would get by the random walk, and taking that and computing F and G on this pair, looking at the expectation in one case and the expectation in the other case. I want to say how far are these two apart from each other. What we'll show is, okay, once again, omega will give us a control on how far these are from each other. And it's going to be an extremely simple calculation. What we will, the expander, what is called the expander mixing lemma is this. Statement which just says this first expectation, which I call expectation FG. Let's write it carefully. FU GB, U coming from pi, V coming from the random walk starting at U, minus mu F, mu G. How I want to ask how much do these two quantities differ from each other? This is at most omega times. Omega is once again the max of omega 2 and minus omega m times sigma F, sigma G. And what is sigma F? Sigma F is just our usual standard deviation. So sigma F square, where sigma F is just expectation of F square V when V is picked from pi minus expectation of F. Let's write it. Expectation of F, FV square when V is picked from pi. That is basically expectation F square pi distribution minus expectation F in the pi distribution the whole square, the variance. So that's going to be this one. So that's what's called the this is what's called the expander mixing lemma. It says that if omega is small, omega tells you how far these are bounded away from 1. The smaller it is, omega is a number less than 1 now. The smaller it is, this distance between these two is very, very small. So in particular, omega could be 0. Where is omega 0? Omega is 0 for, in fact, if you look at the complete graph. For that, omega will be 0. And for that, it exactly, that is exact. The random step is exactly like walking on the complete graph. Taking mu f, mu g, and the left-hand side and the two quantities in these two are exactly the same in the case of the complete graph, because random walk on a complete graph is like picking two independent things according to the stationary distribution. In which case omega is 0, and in case this quantity is one. And we are saying this, that's not just true for a random walk. This is true. That's not just true for the complete graph. For any graph, as long as this omega is small, it's bounded away from 1, you can control the error between these two. When we will see this will be this is an extremely useful lemma. We will see applications of this in a couple of lectures from now. We'll actually see how to use this for several de-randomization applications in theoretical computer science, which will just be a consequence of this expander mixing lemma. And proof of the expander mixing lemma, given the spectral decomposition, actually extremely simple. What's the expander mixing lemma? We'll just, how do you prove it? The proof is a simple application of the writing F and G in their Eigen decomposition, according to their Eigen decomposition. So let's write F as summation alpha I vi, G And this is, once again, this is the same thing as alpha 1, the all ones vector, plus I going from 2 to n, alpha I vi. Because I'm separating the two there's one, the all ones eigenvector, and the rest. Similarly, G is going to be written as summation beta I vi, which I will write as beta 1, 1 plus I equals 2 to n beta I vi. And what did we care for? We cared for expected value of fi gj, when you pick I according to pi and j according to a random walk. Right? This is exactly fwg that we saw, random walk. And this, if you write it in the Eigen decomposition, this is just exactly omega I, alpha I, beta I. Let me be a little more. This one, this is, what is this? This is the inner product between summation alpha I vi and w times summation beta I vi, which is the inner product between alpha I vi, and w is in this one. This is summation, therefore omega I beta I vi. These are orthonormal vectors, therefore this is just summation omega I alpha I beta. So omega 1 is the all ones eigenvector, so let's write this as alpha 1 beta 1 plus summation I equals 2 to n omega I alpha I beta. Why am I writing it this way? Let's find out what alpha 1 is. Alpha 1 is the inner product of f with the all ones vector. That's the component. You want to know what's the component was along the first eigenvector, because they're orthonormal, it's just the inner product along the first eigenvector. This is what? This is just summation pi I fi. This is just the expected value of f according to the pi norm, which is what we called mu f. Similarly, beta 1 will be mu g. Therefore, the expression that we care for, fwg minus mu f minus mu g, is in fact exactly equal to summation I going from 2 to n omega I alpha I beta. Are people with me? This is the difference we wanted to calculate. That difference is exact. If you take off the first term from this inner product, it's exactly the remaining term is the error between these two. So it's the absolute value of this. This is less than or equal to omega into alpha I beta I going from 2 to n, because of the way I defined omega. Omega is the largest absolute magnitude given if you knock off the first term. Therefore, this is less than or equal to omega into summation I equals 2 to n alpha I beta I. This, I'm going to apply one Cauchy-Schwarz. This is equality. This is at most summation I equals 2 to n alpha I square root summation beta I square root. But let's look at what is I equals 2 to n alpha I square. This is exactly I equals 1 to n alpha I square minus alpha I square minus alpha 1 square. What is this? The first one is just the inner product of f with itself. The second one, we already saw that this was mu f square. But what is the inner product of f with itself? This is exactly expected value of f square I when I is picked according to pi minus mu f square. This is exactly the way we had defined variance sigma f square. So that's it. So this quantity is equal to omega sigma f sigma g. Yeah, so this is an extremely simple application of the spectral decomposition in terms of the eigenvectors of the random walk matrix. It just tells you that, and it's a very nice statement. It says you could pick the thing to notice in the left hand side. What you're doing is you're picking u and v completely independently from the stationary distribution and computing f and g on them and taking the expectation. The second one, you're picking it correlated fashion. You're picking the first one according to pi, the second one as a neighbor of it according to the random walk, and then taking the expectation. You're saying that these two the expectation things, the first one they are independent, the second one they are correlated, yet the difference between these two expectations is actually very small. And how small it is, it's governed by how small omega is. The smaller omega is bounded away from, the better omega is bounded away from one, you get a better handle on this quantity. Okay, so if you didn't have a graph, if you didn't have a, we will see various applications of this quantity, of this expander mixing lemma shortly. That is, I will do a little more theory. I'll prove Cheeger and Lobach theta function, and then we'll see a couple of applications of what's the expander mixing lemma. In fact, there are a whole bunch of things in theory, like extractors, dispersers, and even the Chernoff bound on the expander walk, all of which can be just got as a consequence of just this expander mixing lemma. Okay. I'll stop with this. I've already taken 9 extra minutes. Any questions?
Did we see what an expander graph is in this course?
I haven't defined what an expander graph is. So the reason this is called an expander graph is for which omega is bounded away from 1. That's the, so for which omega is a constant. Omega is like 1. So it's called, something is called an expander if an underlying graph is called an expander. Random walk graph is called an expander if the omega for it is, say, less than, it's called a 1/3 expander if omega is less than or equal to 1/3. This quantity omega is what actually defines how good an expander it is. The smaller it is, it's a better expander. So it's the best expander if omega is 0. And you are interested in expander. So you can take the definition of expander to be whatever this definition gives. We will see a more combinatorial definition later on, but a spectral definition of an expander is exactly the fact that the maximum of omega 2 and minus omega n is bounded away from some quantity which is less than 1. So say it's a 1/3 expander means this omega is less than or equal to 1/3. Okay. Yeah. Yes.